Hello, this is Paul from Tech. In this video, let's prove Theorem 3.3.4, which is distance formulas in 2 or 3 space. So the first is the distance between a line, between a point to a straight line in 2 space. So suppose I give you a straight line. Outside of a straight line, we have a point that was the shortest distance. Yeah, we do have this formula before, like basic algebra or pre-calculus, right? We will give, so I will introduce a different approach, in a linear algebra. We can use the vector. We can take advantage of the vectors or orthogonal projection, we learned before. The second is another formula in 3 space. Suppose we have a plane, and outside of the plane we have a point. What's the shortest distance of the point to the plane? See, the formula is quite similar, and that the proof method is also very similar. So I will leave the proof of B for you. So let me introduce how to use the vector projection to prove A. So first, let's say A, which is the shortest distance of a point to a straight line. Let me draw a graph for you. First, let me draw a simple graph to show you the idea. No, this is a line. So this is the line, or we simply say this is the line. I use L to describe. So the line is ax plus by plus c equals 0. That's the general equation, right? So we learned. And then outside of a line, we suppose I have a point. This is the point. The point is x 0, y 0. And then what the shortest distance? The distance should be like this, right? From here, to here, should be perpendicular. And I ask what is the shortest distance. So what is this distance? The basic idea is this. Let me pick a point here. This point we call P, and the coordinate is x, y. Therefore, the P should follow this general equation of a line, right? And then I link these 2 points, and then put arrow here. So we do have a vector this time from P point. I have to give so the original P should be P0, right? So let me see. Yes, the original P, the point that we call the P0. So now we should have a vector from P0 point to P. Yeah, you use P, the coordinate minus the coordinate of P0. I know this vector. And then the distance, see, the distance, shortest distance of this should be what? Should be a projection, orthogonal projection of the vector P0 to P, projected to what? To this perpendicular direction. What is this direction? This is the normal direction of the straight line. Remember, this is the normal. If I simply say here, see, this is perpendicular, so this direction should be the normal vector, the normal direction. We learned before the normal direction should be the vector of AB, right? See, this is easy. It's just the AB. So I know this. Therefore, the distance we need to find from here, or I simply say this distance, shortest distance. Let me do this. This shortest distance, the distance D should be what? Should be a orthogonal projection. Should be the normal, right? Of P projection. Projection of the vector P0 to P onto the direction of n, and the norm. The norm is the distance. Is that true? Yeah. And before the previous theorem, we proved the formula for the projection. Therefore, if we find the projection, okay, and then you find that the norm of the projection, which is the distance. Yeah, this is the basic idea. Now let's do calculation. So all we need to find everything, right? So first, the direction, the normal vector we already have, n we already have. What is p0 to p? p0 to p. Yes, I know, which is the point p minus the point p0. That's x minus x0, y minus y0. Yeah, good. And then I find the projection. So the projection of p0 to p onto the normal direction. Okay, the normal. Let me put here. The normal is a p. The projection I do. Yes, I do have a formula. So remember the formula. The formula should be p0 to p dot n, right? Is the numerator. The denominator should be the norm of n squared, and then n. And the first is the coefficient. Okay, so did the coefficient, then comes n, because the projection should be parallel to the direction of n, which is a scalar multiplication. I think you remember this. So I can find whatever. So let's find. Oh, we can simplify first. See, because what do we need is not the projection. What do we need is just the norm or the distance of the projection, right? So I can do a little simplification now. So I directly get the distance d should be the norm of projection p0 to p onto n, right? Okay, so therefore is this. Let me put the formula here. This is just a number, don't worry. This is the vector. Okay, so all this term is a scalar number. So take the scalar number out the side, right? So we do have a property before shows that. So take out, of course, we need to put the absolute value. So let me put the absolute value, which is p0 to p dot this and this absolute value, and then times sorry, here I missed. It's not a square, it's the norm. It's the vector. Okay. So what do we left? The inside is this. It's just the norm. Okay, of n. Can we simplify a little? Yeah, definitely. We see. The denominator we have a 2, right? 2 norm. So I cancel 1. Okay, what do we have? This is the power of 1. The power of 1, I can ignore the 1. So I get a little simple. Should be a fraction. The numerator is a p0 to p dot m. Okay. This number should be absolute value, because distance is always non-negative. Okay. The denominator should be should be not a 0, because it's the denominator. Okay. If it's 0, we'll never talk about it. So now we need to find this. The denominator is easy, right? Because I know n. Okay. So the normal, which is the square root of a squared plus b squared, we already have. And then we need to find the numerator. Okay, the numerator here, right? N is here. plug this vector and this vector inside, which is dot product. Dot product is sum of the products, right? So easy to get. So now this should be this. The denominator by the definition is a squared plus b squared. That's the norm. The numerator is this. Let's see. Okay. What is it? Okay, this number times a plus this number times b, the sum of product. So, which is a times x minus x0, right? Plus b times y minus y0 for the absolute value. Almost. Okay. Because we make xy is just the point that we make, or general point. We don't know what is x, what is y. We have to take it away. So how? I use this result. Now we have to use the point P xy is on the line L. Okay, it's on the line. It means xy should be follow the equation. The equation which is ax plus by plus c should be equal 0. See, try. We need to use this one. Okay, simplify is how? How to simplify? We need to put the x and the y together, right? So you can do this way. I can do another. Change it a little bit. The denominator is still there. Now change the numerator. I change it to, I put the x and y together, which is ax plus by. Because there is a c here, so I can make a c right here. And what do we have left, which is a x0 plus b y0. And I have to plus another c, because the c and the c should be cancelled, right? C minus c is 0. You can see this is exactly the same. I will do this in this way. I can plug this 2 here. So this disappear, right? It's 0. And then we get the result. The result should be this way. The denominator is a squared plus b squared. The numerator absolute value. The negative I can just cancel. So ax0 plus by0 plus c. Yeah, is this the formula? So we check the distance is this. Is this the formula? Okay, you check. Yeah, definitely. Okay, so you can do calculation. Just plug the points to the numerator and then find the norm of the normal vector on the denominator. So this is the proof. And for b is similar, and is similar, exactly similar. Okay, similar for b. I just leave this for you. That's all. Thank you.